So let's get started again. Before that lecture, we had a lecture about the vector cross product. And in order to deal with the moment of a force in vector formulation, it's important to understand the vector cross product. And if you can see here, if I have a body and I have a force here, F, and as a result of that force, I'm going to have a moment about that axis here. Then, in that case, the direction of the moment is going to be perpendicular to the plane of the point O and F. So here, if I'm going to have a plane here, the moment is going to be, the axis of the moment is going to be perpendicular to that plane. And they notice that since the moment is going to be directed perpendicular to that plane, they say that we could express the moment vector as vector cross product. That is why I gave you a revision about the properties and how to deal with the vector cross product. They propose that the moment vector, which is here, equals R vector cross F vector. F, we know F. F, it's here. But what about R? They say that R is the position vector. We remember the position vector. The position vector is a fixed vector relate one point to another. So R here is the position vector. And the definition for R is very important to solve the problems. R is the position vector. It's directed from the point O. O is a point of rotation here to any point on the line of action. So if this one is the vector F, and if you extend the line here, all of that part represent the line of action. So if you have position vector directed from the point O to any point, it could be here, or it could be here, or it could be here, to any point on the line of action. This is important point. It doesn't need to be perpendicular. It could be here or it could be here. And they find out that you will get the same answer. So it doesn't really matter. As long as the position vector is directed from the point of rotation, point O here, towards any point on the line of action. So they find out that the moment vector, it could be expressed by the vector cross product. M vector equals R vector. R here represents the position from the point O to any point on the line of action of the force, cross F. F is the acting force here, the force that caused the moment. And we could use the scalar notation. So if I'm going to have, I have X, Y, and Z, and I have the vector F, I'm going to resolve the vector F into X, Y, Z components, and then I'm going to multiply them by their perpendicular distance in order to calculate the moment. And that is very difficult to do it. Actually, it's confusing, and most of the time, you are going to make a mistake. That is why the proposal of using the vector cross product here, it was successful. So how did they know that if they are going to use the vector cross product to express the moment vector is going to be successful. They make comparison between the scalar notation, which means that here they decompose the forces in all direction and multiply them by the perpendicular distances. They compare the result with the vector formulation. And it's very easy to use the vector cross product compare with the scalar notation, especially in 3D dimension, 3 dimensions. So if you do remember that, we said that the cross product can be written as determinant. So here, instead of C, we are going to put M. Instead of C vector, we are going to put M. Instead of A vector, we are going to put R. And instead of F, we are going to put B. So we say that we could express this as determinant. We are going to get the determinant of IJK. Here we used to have AX, AY, AZ. Here we are going to replace the A with R. And we are going to replace the B with F. So the moment vector equals R vector, which is the position vector, cross the F vector. And since we know since we know Rx, Ry, Rz, Fx, Fy, Fz, if we get the determinant of that matrix here, we are going to get the moment vector. And if you solve this one, I explained previously, we are going to find out that the M vectors equal Ry, Fz minus Rz, Fy, followed by the letter I minus Rx, Fz minus Rz, Fx, followed by the letter J, plus Rx, Fy minus Ry, Fx, followed by the letter K. And like I said that that equations, it has been solved by using the scalar notation to make sure that we are going to get the same answer here. Another good thing about the vector cross product, we have what's so-called transmissibility of a force. So here we have a body, we have the point of rotation, here we have a force, and this represents the line of action. Then that force, of course, is going to cause the rotation about that axis here. And we say that the M equals R cross F. And we say that the R is the position vector from the point O to any point at point on the line of action of the force. So I could say that M naught is going to equal R1 cross F, or R2 cross F, or R3 cross F, or it could be R4 or R5. As long as the position is directed from the point O to any point on the line of action. So we can say that M naught equals R1 cross F. You could use this one, or you could use that one, which is R2 cross F, or you could use that one, which is R3 cross F. And that's the beauty about using the vector cross product. It's not necessary to use a position vector which is perpendicular to the line of action. So when using the cross product, we do not need to know the perpendicular distance from point O to the line of action. It could be any distance here. And now, of course, like the previous lectures, if I'm going to have more than one force and they are going to cause moments, that means I need to calculate the resultant to know the final effect. And if that's the case, if I'm going to have F1, R1, F2, R2, F3, R3, I'm going to calculate the resultant moment of a system of forces. I'm going to say that the moment vector resultant about the point O is going to equal the summation of R cross F, R cross F. So in that case, we are going to get R1 cross F1 plus R2 cross F2 plus R3 cross F3. So now let's start with example here. The example is going to make it clear for you. So as you can see in the figure here, we have a tree. We are going to destroy that tree by using that machine here, which means that I apply a force in order to get rid of that tree. And the point O is going to be the point of rotation through which the tree is going to rotate. And the question is, we need to calculate the moment produced by that force. So that force is going, of course, to produce a moment. We need to know the that moment about the point O. Not only that, but also they want us to express that moment as a Cartesian vector. So here we have a force. We know the magnitude of the force. We know the point A. We know the point B. And here is the point of rotation. We have x-axis, y-axis, and z-axis. So since the problem is 3D, we say that it's convenient to use the vector cross product. So we are going to say that the moment equals R vector cross F vector. We need to know R from the figure, and we need to know F from the figures also. So F is a vector. Do I have the F vector here? The answer is no. I have only the magnitude. So I have a magnitude. I need to express the force which is directed along that line into a Cartesian form. Here we are going to use what we have got in the previous lectures. We'll learn how to express a force along a line since I know the point A and point B. So this time I need to know the coordinates of the point A. We'll learn how to get the coordinates. Here we are going to move from the origin. We don't have distance in X or Y. I have only in Z. Then the coordinates of A is going to be 0, 0, 12. The same thing, I should get the coordinates of the point B. Here I'm going to move in X, 4, and I'm going to move in Y, 12. I'm not going to move in Z. So I'm going to have 4, 12, 0. Then, since I know the coordinates of the point A and the point B, I'll be able to calculate the position vector. So the position vector is going to be like that. If you remember that formula, then the RAB, and of course the direction is A from B. It's shown here. You can see the arrow. Even if you don't see the arrow here, you know you are going to pull from that direction. So the direction of the force is going to be like that. So if you calculate the position vector, you are going to find out that you are going to have 4, because 4 minus 0 is 0. And here 12 minus 0 is 12. And here you are going to get 0 minus 12, which is minus 12. So we're going to have 4i plus 12j minus 12k. So now I know the position vector here. So how I'm going to move from the position vector to the force vector? I need to divide by its magnitude and multiply by the magnitude here, which is 2. How to calculate the magnitude? The magnitude is the square root of 4 square plus 12 square plus 12 square. So in order to express the force as Cartesian vector. Here we have the position vector. We are going to divide it by its magnitude and then multiply it by the magnitude of the force, which is 2. If you are going to simplify that formula here, you are going to find out that the force is going to equal 0.4588I plus 1.376J minus 1.376K. And now we only got the value of F. Now, what about the value of R? So we said that the moment vector equals R cross F. And say that R is a position vector from the point A to any point on the line of action. So which one should I use? So here I already calculate the F vector, but I need to know the value of R. For me, I'm going to use a point, but that point, I should know their coordinates. So if I'm going to say that, I'm going to use the distance from here to here. Then how I'm going to know the position vector? I know the coordinate here, 0, 0, 0, but what about that point? So I don't know, it's not given here. So I'm going to choose a line so that I know the coordinates, and as a result, I will be able to calculate the position vector. So if you focus here, you are going to end up with only 2 options. You are going to use that line here. You are going to say that my position vector starts from O to point A. And that satisfies the condition because the distance here directed from O and that point lies on the line of action. Or you could say that I want to use RB. Also, it satisfies the condition as long as the position vector directed from the point O to that point B. So I have to be clever using which point to determine the value of R. So R, it could be, before that, of course, I need to know the coordinates of A. We already calculated, and the coordinate of B. So I could say that M vector equals RA, I choose this one, cross F vector, or somebody else, he could say that it's going to equal RB cross F vector. The one who is going to use this one, it's correct, and the one who is going to use this one here also, it's correct. Now I need to know the RA. Since the vectors between the origin and A, the position vector is going to be 0i plus 0j plus 12k. Since this one is 0 and 0, I'm going to say that RA is 12k. And if I want to calculate the RB, since the position vector between the origin and B, then the RB is going to be 4i plus 12j plus 0k. Since this one is 0, I'm going to say that RB equals 4i plus 12j. Now, I know RA, I know F, or you can use this formula, and in that case, I know RB and I know F. Then I'm going to put them in matrix in order to calculate their determinant. So M vector equals R vector cross F. We're going to use this one, IJK, RX, RY, RZ, FX, FY, FZ. I'm going to put those as it is. Here, if I'm going to use RA, here RX is 0, RY is 0, and RZ is 12. Here, FX is 0.4588, FY is 1.376, and FZ is minus 1.376. Now, I'm in position in order to calculate the determinant for that matrix here. First, I'm going to start with I. I'm going to make a line here and line here. I'm going to say the first part is I times 0 multiplied by this one plus minus 12 times that one here. So I'm gonna go like that. And then I'm going to start with the j element, cross this one, cross that one, multiply this one minus that one, and finally I'm going to use the element k, cross that one and that one, multiply this one here minus that one here. So if we're going to do that, you'll end up with that formula here. We're going to have, of course, this for I, cross this one, that one, this one minus that one, minus this one minus that one. So now I finish from the I. Regarding the j, remember we need to put the minus here first, then cross that one, I'm going to put j. I'm going to have 0 times that one minus this one times that one, followed by the letter j, plus for the element k, cross that one, I'm going to put j, then I'm going to get 0 times that one plus minus 0 times that one. And the answer came to be like that. Of course, 0 minus 0, that terms, it will gone. So finally, we are going to find out that the moment vector equal minus 16.5 I plus 5.51 j. Of course, the unit is kilonewton meter. So I may use that one as well. So I can use RB. And in that case, I'm going to have 4, 12, 0 instead of 0, 0, 12. And if I am going to evaluate that determinant, I'm going to get the same answer. So the answer here is the same as here, even though here I use RA, while here I use RB. And of course, if you want to know the direction of the moment, you are going to use the right-hand rule. You are going to move your fingers. You are going to curl your fingers directed from the RA towards B, and you are going to find out that your thumb is going to be directed like that. So I'm going to give you the chance to ask questions regarding the first example. It's clear? Don't have any questions here? See example 2. So now we are going to solve example 2. Here in example 2, we have more than one force. And it's mean that if I'm going to have more than one force, it's mean that I'm going to have more than one moment. So this time, I don't have only one moment, I have more than one moment. And if I'm going to get that, I need to evaluate the resultant moment, the final moment. And to do that, we say that the resultant moment is the summation of R cross F. So in that case, we're going to have F1 R1 and F2 R2, because I have F1 and I have F2. So here I need to know the value of R, which one should be R and which one should be R here. So the definition of R, again, is the position vector from the point O to any point on the line of the action. And we say that I'm going to choose a point that I know its coordinates. So here I'm going to move from the point O, and here is the line of action. I can use any point, but I'm going to choose point A. Why? Because I know the coordinates of the point A, and I'm going to call it RA. And regarding F2, here is going to be the line of action of R2, but I'm going to move from point O, the origin, towards the point B, because I know the coordinates of the point B. So I'm going to say that the resultant moment is going to equal RA cross F1 plus RB cross F2. So now I need to know F1, F2, RA, and RB. This time, F1 it's already given because, like you can see here, F1 it's already expressed in Cartesian form. And the same goes for F2. F2 this time it's expressed by the Cartesian form here. So in this problem, F1 is given and F2 is given. It's mean I need to know the value of RA and RB. In order to know RA, I need to know the coordinates of A. In order to know RB, I need to know the coordinates of B. So here is RA and here is RB. The coordinate of A is going to be 0 in X and 5 in Y and 0 in Z. Regarding B, you are going to move in the X. The X is going to be 4 and the Y is going to be 5 and the Z is going to be -2. So I'm going to have 4, 5, -2. Then since the vector is from the origin here, the RA is going to be 0i plus 5j plus 0k. But since this one is 0 and 0, I'm going to say RA only equals 5j. And for that one, again, since the vector between the origin and point B, I'm going to say that the vector B is 4i plus 5j minus 2k, like here. So now I know RA, I know RB, F1 is given, and F2 is given as well. And I'm going to have two determinant this time. I'm going to have ijk 0, 5, 0. I'm going to have -60, which is here. This one represents fx, fy, and fz, -60, 40, and 20. Here I'm going to put RB, I'm going to have 5, I'm going to have 4, 5, -2. Here I'm going to put F2, which is 80, 40, and -30. Then I'm going to get the determinant for that part and the determinant for that part. So we expressed them into determinants. And if you are going to evaluate the determinants for that part and that part, you are going to find out that the resultant moment equal 30i minus 40j plus 60k. And also, if you want to know the axis of the resultant through the values of I, j, and k, I will be able to know the location. This one is positive, and this one is negative, and this one is positive. That means the force is going to be located here. Since it's positive, since the I is positive, it will be here. Since j is negative, it's going to be there. Since the k is positive, it's going to be up. And also, since this one is a vector, I can calculate the value of alpha, beta, and gamma. How I'm going to do that? I'm going to divide the moment vector over its magnitude to get the unit vector, and then I'm going to say that I will be able to calculate alpha and beta and gamma like we have learned from the previous lectures. Okay, so I'm going to stop here. If you have any questions, please ask me.